me to talk about CO2 conversion. So really, for the CO2, Omar already mentioned CO2 capture and conversion. We're talking about really at gigaton level. Okay? And I'm going to also talk about how can we turn this CO2 into a new industry. That's our future chemical industry, and potentially operate at the terawatts level. And of course, for today's symposium, I will also talk about how AI and the machine learning can help us in this sort of transitioning of this new chemical industry. As of today, of course, the global power consumption is roughly about 16 terawatts, and that's causing many of these CO2 emission problems for the past 100 years. And of course, we're expecting this power consumption is going to be increased, right? It's maybe by 2050, this power consumption will be doubled. Okay? And along that process, of course, there will be additional CO2 CO2 emission into our environment. Okay? So that's this number is something to keep in mind. We're living in a society that requires energy at terawatts level. And every year we're talking about the emission of 35 gigaton into our environment. That's every year that's happening, of course, from all the sectors, from our power plant, from our manufacturing site, cement, transport, every sector. Okay, of course, chemical industry as well. Okay, and that's another number to keep in mind. And that basically causing the CO2 concentration is increasing, and it's still increasing every year by 1 or 1.5 ppm. Okay? And we will see that trend for the probably next 20, 30 years, okay? Given we're moving towards the carbon neutral sort of stage, maybe at 2050, right? So this is what the Paris Agreement is talking about. In the next 20, 30 years, we want to head into this carbon neutral. And eventually, by end of this century, we're getting into the carbon negative society. But that being said, the next 20, 30 years is still carbon positive. Okay? We're still emitting CO2 into this environment. That's why the CO2 capture and the conversion business is so important at this moment. We really need to think about, of course, for this particular symposium, we need to think about materials for CO2 capture. Omar already solved this scientific problem. And in the meantime, we certainly want to think about how can we utilize those CO2 and turn that into chemical energy, turn that into useful chemicals. And in the meantime, of course, decarbonize all the sector we're talking about. Yeah. And by doing so, of course, what we're talking about is potentially we're going to transform the current chemical industry. Eventually we're using CO2 as our feedstock. And that is going to be probably another $1 trillion industry we're talking about, right? Okay, so that's why the CCUS, the U side is, of course, we can do the carbon capture, do the sequestration, that's one route. But the U is also very important because that's the chemical energy storage sector. That's the basically base that you can really utilize this sort of waste chemical, CO2, and utilize the renewable energy. Maybe that's from solar, maybe from the wind, and store all those renewable energy into the chemical actual carbon bond, which is as of today, still has the highest energy density, right? Okay, so how can we do that? Okay, and what is the sort of scientific or technical challenges we're facing? Okay, what do we want to do? We want to basically start with CO2, water, and the renewable energy, right? And somehow we want to have this chemical reaction. Okay, we want to turn that to very simple chemicals, CO2, water. Okay, it actually turns out to be two simplest chemical, but it's two chemicals that's very, very difficult to activate. Okay, and as that turn into maybe sort of chemical energy storage, making fertilizer if we put nitrogen over there, and of course we can also think about using CO2 to produce these high value added chemicals, or even pharmaceuticals. Okay, and not to mention the high energy density towards this aviation fuels, right? Okay, so everything is about in the middle, catalyze the chemical transformation. and every chemical reaction will need a catalyst. Okay, that's the key sort of ingredient for this whole CO2 conversion to work. And how to do that? Of course, there are many different ways to think about it. Traditional industry use thermal catalyst. Okay, but of course we know the thermal catalysts give us CO2 footprint. Okay, so I would say in the past several decades, people are looking into how can we use solar energy directly to drive the CO2 conversion. And of course, another sector is basically the so-called PV, the solar panel plus CO2 electrolyzer approach. Okay? So let me briefly show you. My lab has been working on this artificial photosynthetic system for now more than 2 decades now. Okay? Starting from the earlier days of Helios program and towards the first DOE Energy Hub, Joint Center for Artificial Photosynthesis. This sort of artificial photosynthetic device is a device that's really mimicking natural photosynthesis. Typically, this sort of device has a photocathode, a photoanode. You don't need add additional sort of bias. Okay, all you need is sunlight goes into this device. Okay, so that the two photoelectrodes will power a 2-half reaction. Okay, just like in the green leaf, right? You have CO2, water goes in, sunlight goes in, then you make carbohydrates and oxygen. So this sort of artificial device that's developing here at Berkeley is doing the same thing. So we can basically, CO2, water goes in, do this one step, this so-called solar to chemical energy conversion and storage. Okay, CO2 goes in, then somehow the C1, C2 intermediates will come out, plus oxygen. Okay, and that's the sort of the photochemical diode concept we're dealing with over the past more than a little bit over 2 decades. These electrodes, okay, these electrodes looks like solar panel, okay. And if you nowadays we're making sort of pretty much at a 6-inch wafer scale on the photocathode and photoanode side, and this is where the chemistry happening. It's that looks like a sort of photoelectrode, solar panel, but they run chemistry. Instead of the PV is solar to electricity, this device actually, when sunlight goes in, CO2, water goes in, it basically produces chemicals for you. Okay? So that's the sort of the photochemical diodes that's mimicking the photosynthetic activity within the green leaf. That's one way to do it. Okay? In one step, basically, CO2 stored convert into C1, C2 intermediates, while the chemical energy of the is stored in those bonds, based on the renewable energy, right, from the solar. Another popular approach, of course, that's also there are many startups in this sector as well, is based on the concept of renewable energy, maybe from PV, solar panel, and the wind, right, and hook up with the CO2 electrolyzer. Okay. And that basically where you can do the same thing. It's a 2-step process. It's a solar energy or renewable energy to electron. Then electron pump into the CO2 electrolyzer, do the chemical transformation for you. Same thing, in many of those cases, CO2 goes into C1 and C2 intermediates. Okay? 2 approaches. One is 1 step, another is 2 steps. They both have pros and cons. Both approaches moving both in the academic and the industrial sector. And here are a couple of examples that are coming out from my lab. You can see that we can, these are sort of several examples you can see. We can make format, okay, in like 1 liter level, 1 molar scale. Acetate, C2 intermediates. These are all made out of CO2 using our artificial photosynthetic system. Then, of course, this process, okay, the artificial photosynthetic system or PV plus electrolyzer approach, we don't have a way to 1 step to turn CO2 into a very complex chemical yet. Typical strategy is CO2 going to C1, C2 intermediates, then utilize the existing biological catalysis or existing chemical process to further upgrade them. And here I show you 2 examples. We can upgrade them into making PHB. Okay, those are 1 gram of polymer, biodegradable polymer over there. or from CO2. We can even make sugar. This is glucose. Okay? Glucose out of CO2. And this is a true mimic of natural photosynthesis, right? Nature is making glucose, carbohydrates, and now we have a chemical process through this our artificial photosynthetic process to make sugar out of CO2. Okay, so those are all possible. Okay, so now, okay, those are basically in the lab. We're developing these sort of artificial photosynthetic device. Step by step, you make the catalyst, you put on the photoelectrodes, then do the system integration, testing. It's, as Omar already pointed out, it's a very, very sort of long process. You have discover catalyst, you put it into a device, you test it. And we are doing that for the past 20, 25 years. Okay? So we want to accelerate that process. What's the key sort of scientific issue we need to sort of really push this field forward? That is whatever we're dealing with, whether it's the photochemical diodes or PV plus CO2 electrolyzer or water electrolyzer, the key thing is the catalyst. Okay? We need a catalyst that satisfies these conditions. Okay? Non-precious metals, low oil potential. The catalyst, as we know, any reaction, you need a waste energy to activate CO2. In this case, activate CO2 in the water. So ideally, we need a catalyst operate at a thermodynamic potential. Okay, that's happening in many cases in the green leaf. Okay, and of course, we want high selectivity, especially for CO2 reduction. We need high production rates. Okay, and of course, for long-term operation, we need a long-term stability. Everything we need basically an electrocatalyst run at least for two very, very important half reactions. One is CO2 reduction, one is water oxidation. And those are the two half reactions we are very, very interested in, and also it's critical for this new industry. Okay? These are two simple sort of molecules over there. So very recently we were talking about basically launch this activity in Bittermat. Okay? So this is accelerated we call it ICAT. Okay? And I think on the AI side, the most important character is I, intelligent. Okay? It's not artificial, it's the intelligent part is the most important. So it's we're thinking about really trying to accelerate the discovery sort of process. Okay? You can see this is having a couple of steps. Basically, the first step is a machine learning based design for low overpotential, high selectivity CO2 catalyst and the water oxidation catalyst. These are the key bottleneck that really is slowing down the whole sort of community, and also in terms of the commercialization of these either CO2 electrolyzer or our artificial photosynthetic system. So in that aspect, we need to worry about many things. We need to worry about these nanoparticle, which composition to deal with, okay, phase diagram, what sort of surface structure is important, and what is the surface structure over potential correlation. Okay, those really require sort of AI and machine learning to tell us. And of course, we start with automated high throughput catalyst synthesis, and followed by machine learning based structural characterization and high throughput electrochemical testing. Now, if in using that process, basically we hope to accelerate the catalyst discovery using a closed loop sort of scheme. And once a better catalyst is discovered, we can immediately integrate into our system overall artificial photosynthetic device. Okay? So I will give you a couple of examples, actually two examples where the AI and machine learning can help us. One example is our recent collaboration with BASF. I noticed we have some BASF colleagues here today. This is efforts that we're trying to basically solve one of the key problems in the water oxidation side. Okay? In the water electrolyzer, one of the key catalysts, iridium-based catalyst. Iridium, of course, is very expensive. We don't have enough storage on the planet Earth to drive the whole water electrolyzer sort of industry. So we want to replace iridium with other elements. And one element coming out is ruthenium. Okay? ruthenium actually is a good electrocatalyst for water oxidation with even lower overpotential compared to uranium. However, it's not stable. Okay? So our approach is using this high entropy alloy-based idea to stabilize these water oxidation catalysts. Okay? Trying to utilize active site of ruthenium, but meantime using high entropy effect to stabilize the whole thing in the electrochemical condition. But in the high entropy alloy, okay, usually we have 5 elements, 6 elements in these nanoparticles. Okay? Which elements we want to select to start with. Okay? So here's one sort of a small step we are taking. Our BSF colleague actually started using this ML. I think Jeff Needham talked about this in the first section, ML-IP. Really to use this method to calculate, survey the periodic table, calculate this so-called short-range ordering between these two elements. Okay, you can see the range of these different elements calculated in the SRO. And those are in the negative side, that's telling you that these elements can be mixed together. If in the positive side, those elements will face separate. Okay? But for high entropy alloy, we're trying to sort of pinpoint which element we can start to mix them together, okay, in the nanoparticle form. Okay? So here's one example. You can see actually you can survey all those exotic elements, including those non-trivial elements like scandium, titanium, chromium, which is very, very difficult to make in the nanoparticle metallic form. Okay? But that tells us, okay, you can see a region of these multiple elements where we're going to plug in our experiment efforts. Okay? So we're starting to basically, I think that little square over there is something our initial sort of testing is going on, okay, in those 5 elements mixing. And I think we have lots of sort of efforts to be done over that direction as well. Okay, so that's one basically guidance in terms of which composition, which structure we want to target. Then of course we have to worry about automated synthesis platform at Molecular Foundry. We have a couple of robots that's used to make these metal nanoparticles in a high sort of throughput manner. Okay, that's one platform we are going to have access. And very soon, this high entropy alloy nanoparticle deposition system is going to be installed in my lab. This is 5 elements that we can basically do the simultaneous sputtering. And this is a system that we're designed to make those non-trivial high entropy alloys. Make like putting in scandium, titanium, chromium elements, which in the conventional solution synthesis you are not able to make. Okay? So this is going to be very powerful deposition system to use. Okay, so now discovering catalyst is, I don't think it's an easy task, okay, because the electrochemical process is highly dynamic. This is not a static sort of structural over potential reactivity correlation. These catalysts and the electrochemical process are constantly evolving. So we do need, again, in this case, is a big data assisted multimodal operando characterization and the electrochemical condition. This using, you can see a range of these facility, 40 STEM, I think in Maria Chan's talk about 40 STEM as well. X-ray absorption, XPS, all these different beamline technique will give us a huge amount of data and operating conditions so that we can identify these structural descriptors. Okay? It's probably not going to be 1, probably going to be 5, 10. So that's the data sort of collection process. That's related to the coordination number, related to the crystal structure, surface facets. Many of these structural descriptors need to be identified. Just give you one quick example. For the 4D STEM, and the electrochemical bias, you can generate lots of these data, okay, in the 2D scan and all these electron diffraction pattern. Easily one section, within like 1 hour, you have generated several gigabits of a data set. Okay, all these diffraction pattern on these very well-established copper nanoparticle catalysts. They are evolving under electrochemical bias. So their diffraction pattern is also evolving. So we collaborate with Emo Hans group at Rice University to do this image recognition and the clustering. And that tells us which facet or which direction, what's the crystallinity correlate to the reactivity. Okay? And this is basically the machine learning-based image grouping, and that tells us all these which grains is correlated to high activity of CO2 conversion. Okay? And this very soon this paper will be in print in Nature Catalysis. And follow that. Okay, follow the structural dynamic characterization using machine learning and AI guidance. Of course, there is the next thing is high throughput activity screening. Okay, we are going to use this scanning electrochemical cell microscopy to look at the composition over potential correlation. Okay, and that's another high throughput characterization technique that we need. Again, if we identify a good catalyst, that will be placed into the electrolyte. Okay. Now I want to close by using two slides I borrowed from my colleague Henry Edward from the LISA, that's the Energy Hub Phase 3. Just show you how the chemical industry can be transformed. Okay? And this chart, this petrochemical sort of chart, tells you almost all the petrochemicals are contained in 95% of all the goods we are using. Okay? For all of us, okay? From your cell phone, from the aviation field, everything polymers. And of course, you cannot read all these small fonts. Of course, current industry is based on this crude sort of fossil fuel, right? But intermediates, you can see, it's all C1, C2 intermediates. Okay, that's from the fossil fuel. But I think the key message here is all those intermediates, C1s like ethylene, C3, C4, even methanol, formaldehyde, all these C1, C2 intermediates can be produced from CO2 and the water and the sunlight. Okay, so that's the new industry that we're looking at in the next sort of another 20, 30 years. Okay? And here you can see that if we replace that, you can sort of remove all these carbon footprint in many different steps: plastics, aviation fuels, e-methanol. Okay? And that, of course, fundamentally changing the foundation of the existing chemical industry, and that's a new chemical industry we're talking about, maybe when we're reaching the sort of carbon neutral society by the 2050 time frame. Okay? So with that, I want to conclude. Thanks for the invitation. Okay? Thank you.
So I think we have time for a question. Is there anyone who can ask a question after that incredible vision of the future? Okay, since you haven't asked I don't want to, but okay, since you haven't asked a question before, I'll give this to Christian, who I just met.
Okay. So I have a question sort of in the realm, since we're here about also applying this in the future and stuff. One could imagine that there will be for quite some while resistance to actually implement this new industry. Would be there some way to think of, if finally everything collapses, to implement it really fast? Or is it something where we need to build it up over 50 years?
Yeah, that's a very good question. The chemical industry transition will not be overnight. It's not going to be overnight. It will take several decades. Okay. So right now, all these CO2 electrolyzer, all these artificial photosynthesis systems, they are coming out from lab. Now we're seeing many of these startups is starting to do related, sort of trying to commercialize this methodology. But that will take actually industry to basically take in this new technology. And I'm a believer that is the existing oil industry needed to transform their chemistry. Okay, so it's their business opportunity, and it's only these oil industry can do that because they have the money, they have infrastructure. All they need to do think about is transform their feedstock. So, but that will take decades to do that.
Okay, so maybe Alexis, a quick question, and then we'll go on to our next.
Sure. So, quick question. One of the products you can make relatively selectively from CO2 is ethylene.
Mm-hmm.
And even if you imagine Faraday efficiency of 100% to ethylene, at 2 to 3 cents per kilowatt hour, it's uneconomical just on the power basis. It's not until you get to a penny a kilowatt hour. And the projections for that to happen, I've looked at this, are somewhere beyond 2035. Now,
Yeah.
how do we get industry to adopt that? Because if you can make ethylene, you can build up a lot of what you showed on one of your next to last slides.
Well, I think this is a tough question for basically for the scientific community as well. That's why I keep saying the identify key catalyst here is the key. Right now, of course, you talk about ethylene production, its cost is too high. Why is too high? It's because of over potential is too high.
Right.
Okay, we're wasting all the time. You talk about, you are seeing some startup or people are talking about claiming CO2 electrolyzer doing great stuff, converting CO2 to ethylene, but catalyst is still the key problem. Okay, that's why we want to have this ICAT accelerated discovery efforts. If you have a catalyst wasting 1 volt to convert a CO2 to ethylene, of course it's not going to work. So here, in order for this industry to work, we do need a sort of disruptive catalyst to appear. And for that disruptive catalyst to appear, I feel doing our sort of traditional way, try and error, is too slow. Okay, this is a common message today, right? We need a fast, we need a faster. Okay, so we need a catalyst that's operating at a thermodynamic potential. If the catalyst is operating at thermodynamic potential, I think cost will come down. So that's, of course, it's related to also the renewable energy cost has to be come down too.
So that's the vision of ICAT, actually, for BitMap, right? How do we accelerate the production of catalysts so that the cost will...
Yeah, I want to briefly mention for water catalyst, water oxidation catalyst, and the CO2 catalyst, in the past 5 decades or so, over potential, the needle on over potential hasn't moved a single bit. That's the problem.
Very small.
So
Yeah,
hopefully AI to the rescue,
Yeah.
we'll see. Okay, so we have had 2 well-established luminaries, and now we're going to have a talk from a future luminary.